Come on. Okay. Now, this is something that I've been getting some questions about, so I want to address the entire class. Um, so, as we all know, starting next week, so after Labor Day, so on September 8th, those classes that were originally scheduled to be in person, um, so unless there's some change over the next week, unless there's some announcement by President Bennett, so those classes that are in person will start meeting in person starting after Labor Day, so on Tuesday, September 8th. That is not this class. So when it was determined over the summer which classes would be online and which classes would be uh, uh, hopefully face to face, I made a decision during that time that these sections of 102, and in fact all of my classes of any kind, would be offered online. And the reason that I did that was that I anticipated that there would be some kind of change in format for the university during the semester because of the evolving situation with the pandemic. That would cause switching from face to face to online or vice versa, and I didn't want that kind of disruption. So I decided to have one format all semester long for consistency's sake. The other concern was that, um, as you should all be aware, for in-person classes or any other activities happening on campus, there are health protocols in place, and I had little confidence that in a class this large, with actually exactly 100 students enrolled in these two sections of 102, I felt that the probability of every single student following those health protocols all semester long was rather low, um, and I didn't want the headache. So I or the risk for any of us. So again, online all semester long is the choice I made for this class. So there's been some confusion as to, since all classes are online right now, and some will be going to face next week, and others will not. I just want to make that clear. This one will not. This is a format that we have all semester long. You can check in SOAR if you look at your class schedule, and under the room, if a room is listed as online or chat, that is a class that will remain online for the semester. Whereas if there's a classroom put in there, that's a class that is supposed to start meeting face to face beginning next week. But obviously, it'd be a good idea to check with your instructor just to make sure. But that's how it's listed in SOAR to help you distinguish between face to face and online. The other thing is faculty have been with classes, some classes going to in person in 8 days. Directors have asked faculty to remind students to familiarize themselves with the health protocols, since now they're going to be very important to stick with. And this was actually brought about by a concern on campus on the part of some students who, according to their major anyway, really should have known better, was that they were in close contact with an individual who had tested positive, and they did not bother to communicate with Moffitt Health Center about that. So if you go to USM's website, or it's also in the statement in every syllabus as to the health protocols for those who are attending in-person classes, please get up to speed on them. Please follow them. It's I know this is a situation that I realize that we have varying thoughts about, but there's one thing on which we can all agree. Um, Certainly no one wants this situation. We all want to get through it and return to some semblance of what there was before. And the best way to do that is to take it seriously. It can be very scary when you feel like you might have symptoms, or one of your loved ones has symptoms. It happens often where I've things I've read about in the news where someone thinks, oh, it's allergies, and it turns out not to be, and then someone gets infected, and it's a particularly serious case. It's aside from even people who have recovered have lasting symptoms even after the virus has left. So it's very important that we all exercise some caution, and concern for others, and that is the best way forward. There is no good way forward, but that is the best way forward of all the possibilities. So again, review the health protocols for the university, and why engage in university activities, while you're on campus. Please do your best to follow them. All right, now I'm going to share my screen here and get into today's homework problems. Okay. Last class, we learned about what a derivative is, what its meaning is, how it is the instantaneous rate of change of a function at a particular point. But what we did not get into then was, if you're given a function like the ones you see in front of you, how do you actually get its derivative? And I gave some examples of how you could get it by using the definition, but you could also see that was too cumbersome. So here we're going to learn some rules that you can follow, so that for various kinds of functions you can obtain its derivative. And that's literally all we're doing today. Is you're given a functions of different kinds, as we see here, and how do you get the derivative? And this is something that you'll be doing all semester long in the context of larger problems. So this is one of the essential skills for pretty much the remainder of the semester. Okay. So here we'll start relatively simple with function g of x is minus 4x. Now, one rule that you can follow, and then this is going to come up quite often, it's called the coefficient rule. Now, I want to explain my notation here. Here we have d over dx. I mentioned that the derivative, like a derivative g of x, is generally be labeled g prime of x. But we can also describe it as dg dx. So d over dx you can think of as an operator that is applied to a function like this c times x here, and the result of it is a derivative. And that's literally what it's called. D over dx is the differentiation operator. You can think of it as a black box. A function goes in, its derivative comes out. So what this equation is saying is, if you have a function like this, a constant times x, you take the derivative of it, it's just a constant. So basically, taking a derivative in this case just strips away the x. So the derivative in this case is minus 4. So anytime you have a number times x, the derivative is just that number. So the derivative of x by itself is 1, which makes sense because if the derivative is how your function is changing as x changes. If your function is just x, then the function and x are the same thing. So they're changing at the same rate. So the derivative would be 1 in that case. So here we have a constant of minus 4. So the derivative is minus 4. So now that I've beaten that horse to death, here we have a second rule for this function. Now here we have a function that is a sum of two terms. And for that we have what's called the sum rule. Now, all this rule is saying, and it's easier to keep track of in words rather than the equation, is that the derivative of a sum is the sum of the derivatives. So if you have a function of multiple terms, now remember, this is adding and subtracting only. I've seen students often mix up properties of addition versus those of multiplication. This is only for adding and subtracting. So if a function has several terms added or subtracted, you are able to take the derivative of each one individually and then add or subtract the results together. So what you can do is you can take a derivative of these two terms, 4x and then minus 5, and then we can go ahead and add those together. So for the first term, 4x, that's the coefficient rule. So in that case, the x is just stripped away, and all you have is 4. So the derivative of this first term is 4. The other term is a constant. So the derivative of a constant is 0. Because what is a derivative? A derivative is a rate of change. Well, if a function is constant, that means it's not changing at all as x changes. So the rate of change would be 0. So we're not going to get any contribution to a derivative from this term. So now we can take the two derivatives that we have, so 4 from this term and 0 from this term, and get 4. Now that's one way to look at it. Another thing to keep in mind is the derivative of any linear function, y equals mx plus b, is just the slope m, because here rate of change would be m, because that's what a slope is, a rate of change, and there's no change coming from b, so it's just the slope. Now, here we have a function of the same form as a previous one. So who can tell me what the derivative would be? Be sure to unmute yourself. 3? Yes, it's just the slope. So we get 3 from this term by the coefficient rule, 0 from this term because it's a constant. All right, so fill that in there. All right. And yeah, so and we're just handling each term individually, adding the results together. Okay, good. Now, actually, for the rest of the time, we're going to be dealing with functions that have various powers of x in them. So another rule is required, and really it's a rule that this lesson is all about. I'm going to move this to a new page. Right, so the power rule, that's something you'll be making very heavy use of all semester long. That anytime you have a function that's a power of x, x to the n, then is nx to the n minus 1, that's a derivative. So the exponent comes down, it's multiplying in front, and then you have x raised to a power 1 less than the power that was given. So we apply that here to minus 3x squared. So the 2 is going to come down, but don't forget, the minus 3 is still going to be there. By the coefficient rule, that's just going to hang around. So that gets multiplied with the 2 that's being brought down. Then we look at the exponent, we subtract 1 from it, and that's going to be the power of x in the derivative. So this is what we have now. So the minus 3 was there before. The 2 comes down. We deduct 1 from power of x. So here's our derivative. But now we should clean it up just by performing all the operations involved. So we get minus 6 times x, because anything to the first power is itself. So x to the first is just x. Okay. Look at another. Also a power rule. We're going to bring the exponent down and multiply with a minus 4. That was already there. And then we deduct 1 from the exponent. And we clean everything up. And we get minus 16x cubed. So bring the exponent down and deduct. And that's true regardless of what x is, whether it's a whole number like this 4 here, or a decimal, or a fraction, positive or negative. Doesn't matter. Any x to anything all works the same way. So now, what would that mean for this one? What would the derivative of this one be? Anyone? Same idea.
We 4.8x to the 3.8.
Yes. Very good. So, oops, sorry, typo in the problem. There's supposed to be a 3 there, but yeah, the way it was actually written, you did it right. So, but to conform to my notes here, yeah. So 4.8 comes down, 4.8 as 1 taken away from it, and then that minus is not supposed to be there. Sorry about that. But yes, you have a right idea. So 4.8 x to 3.8 is what you said, and then the 3 that was supposed to be written in a problem gets multiplied by it, and that's where the 14.4 comes from. Okay. This one. Anybody? Same idea with this one.
Negative 15x to the 6.5 power.
Yes. All right. So 7.5 comes down, multiplied with a minus 2. 7.5 has 1 deducted from it. So we clean everything up, and this is what we have. Okay. Now, one thing that I've seen students have a problem with over years is when we have fractional exponents. So to take a derivative of this, the exact same process is followed. You bring the exponent down, you deduct 1 from the exponent. But I've seen that present problems for some. Just because of not working with fractions correctly. So here, the exponent of 2/3 comes down, then we have x to the 2/3 minus 1. So it's the same power rule at play, but then there's a matter of simplifying this. Now, what you need to do is take the 1, express it over a common denominator. So we have 2/3 minus 1. That's the same as 2/3 minus 3/3. Then you can subtract the numerators, and what you'll get in this case, so 2 minus 3 will give you a minus 1. So that's the result in this case. Actually, I'm going to rewrite these, or I'm going to reformat these fractions so make it a little easier to see. Okay. So x to the 2/3 minus 3/3, common denominator. So you just subtract the numerators, and that's where the minus 1/3 comes about. So it's important to keep in mind that all these things work exactly the same way. So no matter what kind of exponent you have, it's going to be same principle that bring exponent down, subtract 1, but be sure to carry it out carefully. All right, so I'll step through another one. This one has a coefficient involved. So we have the 5 is still there. The 5/8 comes down. And now when we deduct 1 from the exponent again. So now I'm just going to multiply these numbers together. 5 times 5/8. We just multiply the numerators. We get 25/8. And then for handling the exponent, we have 5/8 minus 1, but 1 is written as 8/8, again, to have a common denominator. So now, once it's expressed that way, we can subtract the numerators. And we get 25/8 x to the minus 3/8. So that's how that one works. Okay. So based on that, how would this one go? So same idea as this one, but what would a derivative be? Give it a shot, somebody.
Negative 3/5 x to the negative 4/5 power.
That's right. See why. So we have the minus 3. The 1/5 comes down here. And then we have x to the 1/5 minus 1. So the 1 is expressed as 5/5 for a common denominator. And then we can subtract the numerators. And that is what leads us to minus 4/5. I see we have the same person providing the answers. I'd like to see some of the rest of you give it a shot. I'm not going to give anyone a hard time if they put out a wrong answer. Okay, I don't judge like that, and I find it preferable that someone at least gives it a try, even if it turns out to be wrong, as opposed to someone who, as it turns out, knows what to do, but then remains silent anyway if there's any doubt creeping in there and they feel like it might be wrong anyway. It's not about one's right-wrong percentage. As I've had many people in certain situations counsel me over the years, but people who are the most successful are the ones who make the most attempts, and that leads to a lot of attempts going wrong, but it also leads to attempts going right. So please keep that in mind when I put these questions out there. Now, these next ones, we have x to some power sitting in the denominator. So for functions like these, we cannot apply the power rule to them immediately, not the way they're written. So for certain functions, it's necessary to write the function in an equivalent form so that it actually fits the power rule. So, so with this one, for example, we have 1 over x. So we want to rewrite 1 over x so that it fits the form of a power rule. So 1 over x is the same as x to the minus 1. So now we can use the power rule on this function written this way. So like before, a minus 1 comes down, so we get a negative out here, and then we subtract 1 from the exponent. I've noticed over the years that students make mistakes with dealing with negative numbers. So minus 1, that's going to be minus 2. So you have minus x to the minus 2. Now, you can stop here. You know, that is the derivative. If you want to rewrite it in a way that's similar to the form it came in the first place, you could rewrite it as a fraction. So now x to the minus 2 is the same as 1 over x squared, and we still have a minus. So again, I don't really care between this form or this form. I'm just letting you know that they're equivalent. All right, so if you have x in the denominator like this, to some power, rewrite it to use a negative exponent. Then you can proceed as in the previous problems. But it's still the same power rule. So you're still bringing down the exponent. You're still subtracting 1 from it. Now, so this one right here, and before we had 1 over x, now you have 1 over x cubed. So if you work out 1 over x cubed, what is the derivative of that? And then you can multiply that by 4 because of a 4 sitting up here. So can someone give this a try? So it works largely the same as this. The only difference is that you have this factor of 4 out front, but you're expressing it using a negative exponent, still applying the same power rule. So someone give this one a shot.
Negative 12 to the negative 4th.
That's right. So to show how that's obtained, first we rewrite it. So 1 over x cubed is the same as x to the minus 3. Then bring a minus 3 down, deduct 1 from the exponent. That's going to give an exponent of minus 4. So minus 12x to the minus 4. And that can be rewritten, doesn't have to be, can be rewritten this way. All right, great. Okay. Now, this next one, things get a little messier because here we have a radical. So again, it's necessary to write this in a different form so that the power rule can be used. So when you take the fourth root of x, that's the same as raising it to the 1/4 power, just as square root is raising to the 1/2 power. But because it's sitting in a denominator, I also need this negative. So here is the function rewritten in such a way that the power rule can now be used. By the way, one thing I want to mention, since I have it written here, a lot of students, when they refer to the act of taking the derivative of a function, which is what we're doing all this time, they use the word derive. So they might say, okay, I will derive this to obtain a derivative. And that drives mathematicians like myself nuts. The verb for taking a derivative is not derive. Derive means more generally to obtain a formula, basically to prove that a formula works. When you're taking a derivative, you are differentiating. So we differentiate y to obtain the derivative. So a minus 7 is still here. The minus 1/4 comes down. And then we subtract 1 from the exponent. We multiply the constants together. That's where the 7/4 comes from. And again, we do a common denominator. So minus 1 is written as minus 4 over 4. So we subtract the numerators. And we get x to the minus 5/4. And if I wanted to, I could put it back in a form like this, where it'd be 4th root of x to the 5th. But again, that's really not necessary. This is fine for a derivative. Another common mistake I've seen is with problems like this, where you can't apply the power rule right away, that you have to rewrite the function first and then take the derivative. That students sometimes forget it's a two-step process. They may go ahead and correctly rewrite the function, but then they forget to actually take the derivative of it. So make sure that a differentiation rule is actually applied and before leaving as your final answer. I mean, yes, I'll give partial credit, but you're throwing the rest of it away. So this one, it's also necessary to rewrite the function. So before we think about taking a derivative, how should this function be rewritten so that you can use the power rule? Someone tell me. How do you express this?
Just 1 over 8.
Oh, if the 8 was sitting here in the crook of a radical sign, then you'd be right. But 8 is as a coefficient being multiplied out here. So this right here is just an ordinary square root. So what would it be in that case?
X to the 1/2 power.
Yes. All right. So the way the function is rewritten is 8 x to the 1/2. So yeah, it's not exactly the same as this situation. Notice there's a tiny 4 sitting here, like right in the radical sign, but not in this case. So So be sure to pay attention to your font sizes. Okay. Now, so now in this form, we can go ahead and take the derivative. So what will we end up with in this case? You don't even have to simplify it. We could do that at the end.
4x to the negative 1/2.
Yes, that is right. So to show how that comes about, so we have the 8, the 1/2 comes down, and then we subtract 1 from the exponent. The -1 is expressed as -2/2. Wait, I have a formatting issue here. That should not be a fraction. Okay. So then we can subtract the numerators. 1 minus 2 gives us -1/2. So then if we clean everything up, that's what you get. That's what you said, 4x to the minus 1/2, which can be rewritten this way, because x to the minus 1/2 up here is the same as x to the 1/2 down there. And then you can rewrite that using a radical sign. But again, this is perfectly fine as a final answer. Okay. So this assignment, lesson 2-3A, has quite a few problems in it because a lot of practice is required. Since there'll be problems all semester long where you need to take derivatives in this manner. So it's very important that you get that skill down. So now that we've come to the end of these problems, does anyone have any questions about taking these derivatives? Okay, I will stop the recording here. So if you have any questions you want to ask offline, or well, still in this meeting, but outside the recording, I will stick around for that. And come on.